Okay, so previously we've seen how Riemann sums help us approximate areas under the curves of functions, and that taking the limit as n, the number of intervals, goes to infinity, will give you the exact area under the curve. This is what we will define as the definite integral of the function f. Right, so here's the formal definition. If you have f of x to be a function that's defined on a closed interval from a to b, then the definite integral, which is denoted in the following manner, so I'll draw the symbol here a bit bigger, kind of looks like an elongated S. This is equal to exactly that limit when we take n to infinity. Right, so again, it's the same exercise, right? You're dividing it into many, many rectangles, and my rectangles don't look nice, but you get the picture. And you're gonna get the exact area under the curve, provided this limit exists, of course. If the limit exists, then we say that the function is also integrable on the closed interval from a to b. In our course, we don't necessarily need to worry about whether or not the function is integrable. Most of the functions that we will consider are going to be. And really, as long as a function has only finitely many discontinuities, then it should be integrable. Now, let me just go through the parts of the definite integral here. A and b are called the lower and the upper limits of the integral. Right, so they signify where you cut the function off on the left and on the right for taking the area in between them. F is called an integrand, just a fancy word to mean this is the function we're taking the integral of. Okay. And so now that we know that these definite integrals represent these exact areas under curves, here are two integrals. And I'd like you to pause the video first and try to consider for yourself or try to evaluate these integrals. Right? How would you compute the exact values? Right? So we're looking for actual numbers here. Okay, so think about this for a second. Pause the video now. Okay, so how did you do? Did you try graphing these functions? Because if you know what the graphs look like, you know what the functions are, then that will give you an idea of what these integrals evaluate to. For instance, if you look at this function, y is equal to the square root of 16 minus x plus 1 squared. Well, that looks like a circle, right? It's not immediately apparent when you look at it with the square root, but if you square both sides and rearrange terms, you definitely see that it is the equation of a circle with center at -1, 0 and radius 4. And so we know what the graph looks like. That's -1. And 3 is here. And this is the positive square root. So that means we're taking the upper portion of the circle, or the upper semicircle. In fact, it's a quarter circle here from -1 to 3. So this integral is going to be equal to exactly this area in between -1 and 3, which is exactly this quarter circle. So since the area of the full circle is pi r squared, or 16 pi, this means the area under this quarter circle, from -1 to 3, well, is 1/4 of 16 pi, which is 4 pi. And observe here that we didn't even need to use the Riemann sum definition. We only needed to recognize that this function was a circle, and since we know how to compute areas of circles, then we can just divide it by 4 to get the area of this quarter circle. And now similarly for the function on the right here, this is a linear function. And so just plot 2 points. At -4, this is 5. At -2, this is 1. Right, so this integral represents this area from -4 to -2 under this line. And well, for this integral, you can actually use a Riemann sum and compute the infinite limit, right? This is just a linear function. But we can just look at this area as a trapezoid, right? Or even the sum of two separate areas, that of a triangle and a rectangle. Rectangle has width 2, height 1, right, corresponding to this part of the region. And then the triangle has also width 2 and height 4. So this is equal to the area of the rectangle, which is 2, plus the area of the triangle, which is now 4 times 2 divided by 2, or 4. Therefore, the integral is 6. Okay. So again, what these examples are getting at is that if you have an integral and you know what the graph of the function is, if it's a circle or a line, then you don't even need to do a Riemann sum to compute that, right? You can just look at the area and see, using the geometry of the shape that you have, calculate the area. Now, the question now is, what happens, or what do we do, if the function that you have is below the x-axis on that interval from a to b? Right, so in this case, it's the interval from 0 to 2. And it's the same function that we saw in the previous slide, minus 2x minus 3, but now it's below the x-axis. Well, if we look at the Riemann sum definition again for the definite integral, well, if you look at this sum inside, remember that we're really multiplying two things in each term. Delta x, which is the width of each subinterval, or of each rectangle, and f of xi star, where xi star precisely gives you whatever point you're picking inside each interval. So in this picture, we're picking the right endpoint. And f of xi star is the function value at that right endpoint. And that corresponds to the height of each rectangle. Well, so if f is below the x-axis, that just means this is going to be a negative term. Right? So we're adding up this sum of negative times positive, which tells you that this integral is just going to give you a negative value as a result. And in other words, if you have a function who is below the x-axis, then really you're still computing the area here, right? The sum of the areas of all these really thin rectangles. However, you're computing them in such a way that you're considering them to be negative. And so in this case, we can do the same thing that we did in the previous example. It's minus 1, minus 2, minus 3, 4, 5, 6, and 7. Break it up into a rectangle and a triangle. and add the pieces individually, right? So this area is equal to the area of the rectangle plus the area of the triangle. And here we will make the distinction that we will call them the signed area, right? So it's not just the absolute area of the shapes that you're looking at, but if it's below the x-axis, it's negative. So this is -6 plus, okay, so again, this is 4 and 2, so this is -4. So -10 here is the exact value of this integral. And now this extends to functions where some part of it is above the x-axis and some part of it is below. And for us to compute this integral, for instance, if this is a, b, and c, actually let's just give numbers here. If this is 0, 3, and 5, then the integral from 0 to 5 of f of x dx is equal to, well, I give you here one of the properties of definite integrals. We have a list of them, but this is one property that will help us here. It says, if you have an integral from a to b, since we know integrals are just areas, then you can split the integral up into two separate integrals. One for the area from a to c, and one for the area from c to b. And that tells us that for this specific example, we can do the integral from 0 to 3 separately from the integral from 3 to 5. Right? And so what you'll get here is something positive plus something negative. And we will call this the net signed area. And I don't really want to say under the curve, right? Because it's over the curve if the curve is below the x-axis. So you can think of this as the area in between the curve and the x-axis. Right? So it's the net signed area where we take negative if it's below, positive is above if it's above. So I will leave you here with one question. Can you evaluate the integral from 0 to 6 of f of x dx, where y equals f of x has the following graph, right? So it's this graph shown on the slide, where these curved segments are circular arcs, right? So this is a circular arc. Right, so it's a quarter circle from 2 to 3, and this is also a circular arc. Okay,